Hi guys, welcome back to Data Every Day. Today we're looking at a data set of engineering students, graduate students, and we're going to try to predict the salary of a given student based on a bunch of features from the student. So at the end here we have salary, and this is what we're trying to predict based on we have some personality trait features, some test score features, and some basic features about the student. So let's hop into the notebook. I'm going to import NumPy and Pandas for working with the data, and then we're going to use the train test split function and standard scalar from sklearn for pre-processing. I'm also going to be using two models today. One will be a simple linear regression model from sklearn, and the other will be an extreme gradient boosting model from XGBoost. So they're both regression models, but the second one is much more powerful than the first, so hopefully we'll be able to see an improvement by using a more complex model. So let's get started. I'm going to import the data using pandas.readcsv, and we got to pass in the file path to the CSV file, which we can get up here. So I'll paste that in, and we can take a look. So here's our data. You can see immediately we can't see all the columns because this 34 columns actually surpasses Pandas' default limit for how many columns you can see at once. So up here I'm going to go in and type pandas.set option max columns none. And now if we reload data, we should be able to see all of them. So it's sort of split into different sections. First we have just some regular standard features just about the student, where they come from, what they're specializing in, etc. Then we have over here, I believe these are test scores. Actually, we can check here to double check. So these are everything from here down to civil engineering are like quantitative test scores of some sort. And you can see that missing values, meaning the student did not take that test, have been encoded as a -1. And then we have the big 5 personality traits that were tested for as well. And so these are a measure of the student's personality. So finally we have the salary, which we're going to try to predict. And we can get a little more information about the data by typing data.info. And you can see from here, it looks like, based on this, that we have no missing values. However, that's because they have been encoded as -1s and not as actual, not in numbers, NaNs. So there are some missing values in here. We're just going to have to encode them properly when we get to pre-processing. There are also 7 object columns, and we're going to have to encode those in some way. And you probably see them here. A number of them look like nominal columns, meaning they're categorical, and the values within them do not take any particular order. Alright, so let's start pre-processing. I'm going to create a function called preprocessInputs that's going to take in a data frame. It's going to make a copy of the data frame, and then at the end it's going to return that data frame. So right now all this does is copy our data frame over. Let's call it onData and store the result in X. So X is going to be our processed version of data. And currently it's just a copy, but now as we add pre-processing steps into this function, we can see the result here. So the first thing to do, I guess we could go column by column here. The ID column. So I want to drop that. Right off the bat, I'm going to drop the ID column because these are unique identifiers for a given example, for a given student, and they don't have any meaning in terms of salary, right? These are just random numbers. So they're not giving us any actual information that can be useful for making the predictions. So we're going to drop the ID column. Drop ID column, and we can do that with df.drop ID, and we're dropping from axis 1, which is the column axis. Alright, so it's gone. So then we have gender, and so I'd like to, at this point, take a look at how many unique values we have in each column, because that will determine how we're going to encode these categoricals. So I'm going to get a dictionary that's going to map a column to the number of unique values in that column, and you can get that from taking the length of x subcolumn dot unique. So you'll get the unique values in the given column, and then take the length to get the number, and then that's going to be for every column in x.columns. And so here we can see all the columns and how many unique values we have in each column. And so the reason I'm looking at this is because the gender column has only 2 values. In addition, the college tier only has 2 values. However, college tier is numeric, so we don't have to encode it. It's already encoded as numeric values. But the gender is categorical. So because it has 2 values, the best way to encode it is binary encoding, which just means we set one value to 0 and the other value to 1. So let's do that. So binary encoding, and we're going to take the column, which is called gender, and set it to the same column, but we're calling replace on it, and we're going to pass in a dictionary that's going to perform the mapping for us. So we can send female to 0 and male to 1, like that, and that will actually apply this mapping to every element in the gender column. So now you can see we've processed it, and now we have 0s and 1s instead of Fs and Ms. So next we have the date of birth column. So I'd like to do date encoding. So for the date of birth column, a nice way to encode dates, one way to do it might be to just create this as an ordinal feature that measures recency, and have the oldest date as the lowest number and the most recent date as the highest number. But there's a problem with that in that you lose some of the seasonality and cyclical nature of a date, like the month, which represents time of year. So we can get more information out of this column by just taking out the year, taking out the month, and taking out the day, and putting them in their own columns. And we can do that using, well, there's a few methods you could use, but a nice function that Pandas gives us is toDateTime, which we pass in a column, let's say DOB, and it converts it. You know, if we just take a look at this originally, it's a string column. These are strings. And this, when we called toDateTime on it, they look very similar. However, you'll see the data type has changed to datetime64. And so what's nice about datetime64 object, if we wanted to grab just the year from this, for example, we want to apply a function that's going to grab the year off each x, this being a given x, x being one of these. Then the best way to do that would probably be to say x evaluated or indexed at 0 through 4, and that would just get the first 4 characters. However, this presents problems, especially if you have some unconventional dating formats, or if the months are not always in 2-digit form, then you get some issues with this. So a better way to do it is to actually instead use the datetime column, and instead of applying x 0 through 4, you can just do x.year, and that will actually get you the year as well. And even better, it gets it to you as an integer instead of as a string. So we're going to use this format, this way, to encode the dates. And what I'm going to do is create another function up here. No, actually, I won't make a function. I'll just do it right here. We'll start off by taking our DOB column and turning it into a datetime column. So pandas.toDateTime of DOB. And then once it's in a datetime form, I'd like to create 3 new columns. We'll call it DOB year, DOB month, and we'll do DOB day. And each one of these is going to take the original DOB column and apply a function to it that for a given x will return x dot, in this case year, in this case month, and in this case day. And so now we'll create 3 new columns out of the original column. Then when we're done, we can drop the original column since we've taken all the information we need out of it. So df equals df.drop dob from axis 1. Alright, and now if we take a look at this, you see our DOB column is gone, but on the end of our data set here, we have each new column, the years, the months, and the days encoded as integers. So it's going well. All right, so let's continue. 10 percentage, this is a percentage value. This is already a numeric variable. There is no need to encode this. 10 board, so this is a categorical variable. You can see these are all different, they belong in different categories, and there's also no ordering between them. They're all independent of each other. So we're going to reserve this for one hot encoding. And we can get so basically, let's take a look at this. What I'd like to do is, this gives us a lot of information, but it's a little excessive. I'd like to know actually just the number of unique values in just the object columns, not just all columns. So I can get that, instead of doing x.columns, I'll do x.select dtypes object.columns. And so this will get the column names from just the object columns, and then it'll give us a column matched to how many unique values are in it for each of those object columns. And you can see there's actually only 5. So 10 board is one of them, 12 board is another, and if we look into those, you can see these have values that take no ordering between them. So we know both of these are nominal features, meaning there's no order between the values. Then we have degree, and there's 4 values in here. And let's take a look at that. So I'm going to take x sub degree, and we can get a look at how of the actual values inside with dot unique. And you can see that there are no orderings between this either. I mean, you may be able to argue that one is greater than the other, but I wouldn't say that they're explicitly ordered. So we're just going to leave it as a nominal feature. And then for specialization, which comes next, this also has no ordering between the values. And last is college state, which has no ordering between the values. So all of our categorical features are nominal, meaning there's no ordering between them, between the values within them. So they're all candidates for one hot encoding. And for one hot encoding, we'll use the pandas.getDummies function, and we're going to take in a given column. Let's use degree, for example. And we get the dummies for degree. It'll send each unique value to its own column, and we'll have a 1 in the spot that represents the original value of that example. And all the rest will be 0. So over here, you can see we have btech all the way down. So here we have 1s all the way down in the btech column. And then we're going to create a function that actually does this for us. So up here, I'll call it one hot encode. It's going to take in a data frame and the column we'd like to encode. And it's going to start by creating a copy of the data frame. And then it will create our dummies. And we get this with pandas.getDummies. And we're getting the dummies for df subcolumn. Now I'd also like to add that we can include a prefix here. Let's make it the same as the column name, and that will just add degree to the beginning of each of these columns so that we know where these columns originally came from. So in here, in our function, I'm going to include a prefix that's just going to be equal to the column name we pass in. And then once we've created those dummies, I'd like to actually put them onto our data frame. So we can use that with pandas.concatenate or concat, and pass in df and dummies. And we want to concatenate them side by side, so axis 1. And then finally, we can drop the original column from which we created the dummies, since we've taken all the information out of it, and return the data frame. Now we'll use this down here. So for one hot encoding, so I want to grab the names of all of these columns. So here are all of our categorical columns that we'd like to one hot encode. And I'll say for each column in a list of them. Now let's just go through and clean this up a little. So all right. There we go. And for each column in this list of categorical columns that we'd like to encode, we're going to call one hot encode, which is our function we just wrote, passing in data frame and the column that we're iterating through. Now if we run this and take a look, you can see at the end we have all these one hot columns that came from the original columns that we one hot encoded. And you'll see that now we no longer have any object columns to deal with. If we look at x.select dtypes object, we have no more columns. So we're almost done. The last thing I'd like to do is worry about these missing values. So first thing I'd like to do is change these into actual missing values. So fill, we'll say encode and fill missing values. So we're going to take, we're going to encode them by saying df equals df.replace, replacing all negative ones with numpy.nan. And once they're in nan form, if we look at this now, you can see we now have nans. And what's good about the nans is we can now fill them with a fillNA function. df equals, well actually what we'll do is we'll get a list of the missing columns. These are columns with missing values. And that will be a list of columns for every column in df.columns if df.isNA, so the isNA matrix returns a true false. Yeah, let's look at it. x.isNA looks like this, and we'll have a true in a place where there's a missing value. We can then sum over the rows to get the number of missing values in each column. And so we're going to take that, sum over the rows, and then index that with column. So just looking at the column that we're on in this iteration. And if that value is greater than 0, we'll put it into our list. And so missing columns at the end of this will have all the columns that have more than 0 missing values. And then what we'll do is for each column in missing columns, we will fill it with the mean of that column. So we'll fill the missing values using, we'll say df sub column equals df sub column dot fillNA, and fillNA will fill all the missing values in that column with a given value, and the value we're going to give it is the mean of the column. There we go. So now when we run this, we should see the sum of this. If we sum over it again, now down this way, we'll get the total number of missing values, which is 0. There are no more missing values in our data, and you'll see that the original missing values have now been filled in with the means of each column. There are other ways to fill values. Mean is more of a basic one, but if you want to take a look at some more advanced ways, feel free. And I'd like to now split the data frame. So I'm going to split df into x and y. So y is going to be what we're trying to predict, and that is the salary column right here. So we'll say y equals df sub salary, and then x is going to be all the rest of the data. So df.drop salary, and we're dropping from axis 1. And then down here we'll return both x and y instead of just x. So we'll get back both. Now you can see that x is stored as most of the data, and then y is going to be just the salary column that is no longer here. Alright, and the last, well, second to last step here is to do a train test split. So now we're going to give 70% of the data to the train set and the other 30% to the test set. We can do that with the train test split function from sklearn. We pass in x and y, specify a train size of 70%. It will shuffle the data as well, so that's on by default, and we'll include a random state to ensure that the shuffle and therefore the split is always done in the same way. Then we'll get back 4 new sets of data from that, which will be xtrain, xtest, ytrain, and ytest. And let's return those 4 sets of data instead of just x and y. Alright, we'll take a look at xtrain, which should just be 70% of x, and ytrain, which should just be 70% of y. So you can see the number of rows has gone down, but we still have all the information here. Alright, so I'll just remove these. And the last thing to do is to scale the data. So right now, all the columns take on varying ranges of values. If we look at this more closely, xtrain.describe, or we can say .mean. These are the means of each column. You see they're all over the place, as well as the variances. They're all over the place. So I'd like to standardize that using a standard scaler. Scale x. So our scaler is going to be a standard scaler from sklearn, and we're going to call scaler.fit on the train set, just xtrain. And then we're going to transform both xtrain and xtest using the fit we have just to the train set, using scaler.transform. And the bottom one here is xtest. Now we only fit to the train set because we want to sort of assume we don't have access to the test set while we're doing all this pre-processing. And now if we run this, we will get back a numpy array for xtrain, which is fine. All the information is here. It has been scaled, but we can't see it very well. So I'd like to turn it back into a data frame using pandas.dataframe. And since we're creating a new one, we should specify the column names to be the same as x.columns. Alright, now we'll run this one more time. And xtrain should now be a data frame with its columns scaled. You can see they all take on similar ranges of values. If we look at the means now of each column, they're all very close to 0. And if we look at the variances, they're all very close to 1. So that's what the standard scaler does. It sets the means to 0 and the variances to 1. Alright, and I guess now we're ready to train. So let's start training. So first thing I'm going to do is use a basic linear regression model. And linear regression model is it's a good model when you can accurately predict the value based on a linear combination of the elements in the dataset. And that's not always possible. You can't always get a good fit using a linear model, but we'll start off with linear regression from sklearn. So I'll call it lin model. That's going to be linear regression. And we'll fit this model to just the train set, so xtrain, ytrain. And then we'll print out the result. So if we call model.score, I'll say linear R2. That will be linModel.score. And so if you're using a regression model from sklearn and you call the .score function, it will return the R² score, which is a measure of how dispersed the data is around your fit. And it's a good way of getting a sense of how your regression model is performing. We pass in the test set here, and we'll get back the R² score in lin R2. So we'll say linear regression R² score. We'll display it to 5 decimal places and format that with lin R2. And this is a really, really bad R² score. So R² score can take a maximum value of 1, and it generally takes a range of 0 to 1. But if it's a really bad fit, it can go deep into the negative numbers. And you can see that here we're getting a really terrible fit. This is saying that our model is basically failing to do the job because it's just so negative. So let's see if by using a more complex model we can improve the performance. And we're going to use the extreme gradient boosting XGB regressor. So that's from XGBoost. And the XGB regressor is a much more powerful model than just linear regression. It's actually an ensemble model, which means it combines a bunch of different models to make the predictions. And so I'll call this XGB model. That'll be the XGB regressor. And so now we're going to fit this one to the train set. And we'll get back the XGB R² score from XGB model.score on the test set. And then we'll print out the results. So this is XGBoost R² score. Also displaying here to 5 decimal places and formatting with XGBR2. And this one just takes slightly longer to train, but you see our R² score significantly improved, even though I wouldn't say this is a fantastic R² score. You know, oftentimes it is limited by the kind of data you have. However, if I were to go try to absolutely optimize the performance, I would try out a whole bunch of different models. So this is just sort of a demonstration to show you that using a more complex model can often give you better results if your data is sort of complex. Especially if you have a high number of columns, using a more complex model like gradient boosting can improve your performance. So that will sum up today's video, and thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. So I'll see you guys tomorrow. Have a fantastic day.